This video is entitled Area in Polar Coordinates. So we're going to look to find how to find area of polar graphs. So let's examine this theorem. So your function has to be continuous and non-negative on the interval, closed interval from alpha to beta. They're just using Greek letters here, which is essentially A to B, like you would think of it for a definite interval with respect to x. Now this is important. This next part is that beta minus alpha must be somewhere between 0 and greater than or equal to 2 pi. In other words, you can't have an integral go from 0 to 3 pi because you have all those coterminal points. You can't do that. It would have to be from 0 to pi. So numerically, even though pi, 3 pi, 5 pi, for example, are all coterminal, you will not get the solution correct to the area unless you use values that where the difference is less than 2 pi. So instead of 0 to 3 pi, you would use 0 to pi. Now they talk about whatever the case may be between like sections. So theta equals alpha, theta equals beta. So the alpha to beta or whatever the values you're measuring in turn, the radian measure which you're trying to find the area of. And r is a function of theta. So let's look at the formula that we have here. I didn't exactly fix these fonts very well because that 1/2 shouldn't exactly be so gigantic there, but that's okay. The area is 1/2, limits of integration alpha to beta, r squared d theta, where r will be a function of theta. And of course this part right here I've already mentioned. Now this is one petal, one leaf. We often will do that. If a problem, there might be one of the quizzes that asks this. If it asks for the total area of the entire figure, I will tell you how many leaves or petals there are, so you don't have to know. In other words, because you're going to be figuring this out one petal at a time, and if we were asking for the total area of this, I would tell you that there were 5 petals total, so you wouldn't have to know that. Now let's take a look. Now the way we handle cosine and sine are going to be completely different. It's because when you put 0 in there, where does the graph start out? And I like to use 0 as my lower limit of integration, even if it means doing what I'm about to do right here. I like to start with 0. But anyway, you put 0 in there, cosine of 5 times 0 is going to be 1. So the graph's going to start actually out here. And one of my previous video on polar coordinates, I showed graphing a function. Well, in fact, I'll show you this one real quick right now. Probably still have it in polar mode. There's one. Okay, that's not this one, but so let me bring this in there. And it was r equals, just gotta clear that out, cos 5 theta. Now let me shrink down this window a little bit. That window is going to be way too large. Make it harder to see the graph. So I'll go like -2 to 2 here. And then I'll go -2 to 2. It's going to be a circle with radius 1, but all right. Now when I hit graph here, I want you to watch where it starts out. It's going to start out, like I was saying, on the far right. And then you can watch the pattern that it takes. I wonder if there's a way to make these calculators graph in slow motion, but that would be nice. But anyway, if you watch it, it's going to start out to the right, make its pattern. There we go. All right. So it started out right out there. I decided to use Maple to graph this one just for the heck of it. When Maple prints it out, or it displays it. It uses P for pi. I don't know if there's any way to change that or not, but I certainly wasn't too worried about it because it was obvious what it meant. So it's going to graph this. So then I want to figure out when it gets back to the origin. Because when it gets back to the origin with that axis here, it's going to create this shaded region right here with that lower boundary. So what it's going to do is going to give me half a petal. So what I can do then is evaluate the integral and find the area and then double that result to give me a full petal. Because they're all symmetrical. I mean, they're all going to, each petal's, so if I'm finding half, there's no doubt that's half of that petal. So you can just double it to get one petal. Now, another way to do it, but I like starting with 0. I think it makes it much easier, is to figure out when it gets back to the origin, and then it's going to take this pattern like around, and then you can figure out the second time it takes to get back to the origin. That would be your limits of integration, and you wouldn't have to multiply it by 2, but I don't consider multiplying the formula by 2 to be anything that inconvenient, so I'd rather just do that. So here's how we do this. So we take, we know we're going to start with 0, and I'm looking for the first time that cosine's going to hit 0, a value of 0 on the unit circle, and it's going to be pi over 2. So if I know that cosine of pi over 2 is 0, and if cosine of 5 theta equals 0, all I do is set pi over 2 equal to 5 theta, and then I solve for theta, so it's going to be pi over 10. So that's how we know what our limit of integration is going to be that gets us back to the pole or the origin. That's how you do it. You just figure out what's going to make it 0, and you essentially set the argument of the trig function equal to that value, and that's it. Let's come down and give this a whirl. Now I've got these worked out, but I think it's probably okay if you just use graphing, the numerical integration properties of a TI-84 or an Inspire CX. I don't like calculators that can do the algebraic integration, but numerical I don't mind so much. The key is you got to get it set up right. Now you can decide how you handle this too. It's up to you. I just take care of it from the beginning, so I don't have to even think about it anymore. Now the formula automatically has 1/2 in it. It was up when I was talking about that gigantic looking 1/2. So that 1/2's always there. That didn't come, that was there. And then now I'm going from 0 to pi over 10, and then cosine of 5 theta squared, and we have to integrate that. So I'll go, it's not too difficult. I'll go through this manually. It's not too hard to work out. So cos squared of 5 theta, we have to bring this identity into play. The integrating identity we've used way back in chapter 8. So actually cosine squared of 5 theta equals 1 plus cosine of 2 times that, which is 10 theta all over 2. Now the 2 is going to cancel this 1/2, so that's gone. So now I have 1 plus cosine of 10 theta over 2. That 1/2 could be brought to the outside, and then you integrate the 1, which will be theta, and the antiderivative of cos 10 theta would be 1/10 sine of 10 theta. Remember, antiderivative, not derivative. So I put in pi over 10, I put in 0, so pi over 10 goes in for theta right here, and then 10 times pi over 10 would be pi, so sine of pi is 0, regardless of that 1 over 10, so that's 0, and we still have this 1/2 on the outside. And you put in zeros, for there is going to be 0, sine of theta is going to be 0, and so basically we just have 1/2 times pi over 10 with everything else being 0, so that ends up being pi over 20. And remember, we've already, at the very beginning of the problem up here, we incorporated for the doubling factor, so that is 1 full leaf. And then just in case it would have asked for the total area of the shading, 5 times pi over 20 would have been pi over 4. So to come back up here, that's a circle with radius 1, so the entire area of that circle is pi. So one petal then here, one full petal is pi over 20. So the entire thing's pi over 4 with all of them. That looks about right. So we're saying that 5-leaf thing, 5-petal rose, fills up 1/4, exactly 1/4 of that circle. You kind of smash it all in there. And in fact, you can take all the petals and cram them right into quadrant 1 there. You know, fit all in there beautifully. That's not important. Just thought I'd mention that. Because the value of the answers can kind of vary. Like especially if you've got a problem like this one coming down here in a second. See that 6 in front of that makes it radius 6. So it's going to make the area values larger because it's a bigger circle. Oh, and here's I just want to show you this without, you know, you can put, I'm not going to go through the work again. I mean, all the integration steps will be the same. But here's how I was talking about if you want to calculate it at pi over 10 where it hits the origin, and then what value of it would it get to the origin again? Well, the way you would think of it is to get pi over 10, we set phi theta equal to pi over 2. On the unit circle, the next time cosine will be 0 will be at 3 pi over 2. So I set phi theta equal to 3 pi over 2, and that gives me theta equals 3 pi over 10. So I go pi over 10 to 3 pi over 10 with the 1/2 in front. It's just this time I would not have the 2 in front. That's the only difference. And in fact, I use technology to integrate this for you to show you. Well, I did it. Okay, I did it in the calculator. Now this is using an older calculator without the older TI that doesn't have the integration symbols in there. But it's correct if you do it that way too. But here it is in Maple, and there it is, pi over 20. So you see, and you know, instead of finding that second limit of integration, that's why I like just starting with the 0, and then just making sure I multiply it by 2. So that just gave it one full petal without doubling it. But doubling it was no trouble. Oh, and I just kind of shaded in yellow. That was the actual leaf that we found, or petal was this one right here. Not that it matters. Now sine works a little differently. Sine, you will not ever need that doubling factor under any situation. Because when you put 0 in there for theta for sine, sine of 0 equals 0. So the sine graphs are always going to start at the origin right there. So that you don't have that half petal business. So it's going to start there, and then we just figure out again when it comes back to the origin, using the same kind of technique we did before. So that's the difference between sine and cosine. Cosine, if you want to start it at 0, which I recommend, just double your result. Here, don't double. Alrighty, so we know 0 is the first place that sine is going to be 0, but then the next place will be pi. You know, so for cosine it was pi over 2. For sine, the first place after 0 you get is pi. So if sine of 2 theta needs to equal 0 and sine of pi equals 0, you just set 2 theta equal to pi, and theta equals pi over 2. And there we have it. So now that means our interval is going to go from 0 to pi over 2 with the 1/2 in there from the formula, but not without the 2 this time. We have 6 sine 2 theta squared, so I just kind of, because they're multiplied, I squared the 6 and brought it out, made it 36, and that leaves sine squared 2 theta. So we will use the formula that ends up being a double angle here, the integrating formula. The only difference between this and cosine is it has a minus between them. So sine squared of 2 theta will equal 1 minus cosine of 4 theta all over 2. So the 1/2 times 36 makes 18, and there's a half here, divided by 2 that I bring out will be 9. So then I'm integrating just 1 minus cosine of 4 theta. Antiderivative of 1 will be theta. Antiderivative of cos of 4 theta will be 1/4 sine of 4 theta. Now plug in the values. Pi over 2 for theta Pi over 2 here gives you sine of 2 pi, which is 0. Plug in 0 to the bottom one, you'll get zeros. So you end up with 9 times pi over 2 is 9 pi over 2. Now here it is in the more modern looking calculator. It's not going to give you. Maple would have given me 9 pi over 2 exactly. I didn't put that one in Maple, but that's okay. I did something good enough here. In other words, I got the result from the calculator and then just typed in 9 pi over 2 just so you can see that they're equivalent. So that's pretty much it. So yes, this is a much bigger circle this time with that 6 in front. So you go 9 pi over 2, that's humongous. Well, the entire circle has the area of 36 pi, pi r squared, the radius will be 6. So it's 36 pi, so we're saying basically 4.5 pi is taking up one of those. So you multiply that by 4, that gives you 18 pi. So visually speaking, this entire petal thing, all 4 of them together, take up exactly 1/2 of that circle, because they would be 18 pi. Circle is 36 pi. Once again, not important, but I just like looking at the visual aspect of it. All right, here's one of these either cardoids or limacons. Get confused on which is which. I think the limacon is what makes the loop. Cardoid just the heart shape. Well, I won't be testing you on that, so don't worry about it. Now this one, we don't have to worry about where it starts, that kind of deal with the petals, because it's just one continuous graph. Now you can go 0 to 2 pi. Now 0 is not going to start you right there, though. That's okay. 0, because if you put 0, 1 plus 0 would be 1. So actually it starts here. But then it will make a complete path and get right back to that end point at 2 pi also. So it doesn't matter that it's starting at the point there, don't worry about that. 0 to 2 pi takes care of these kind of graphs, no problem. So you really don't have to think about the limits of integration. That's easy, 0 to 2 pi. The integration's a little messier on this one. If you're doing it manually. Like I said, just a little messier. I don't want to make it imply that it's certainly difficult. It looks like I graphed it in Maple here too. I don't know why I drew the yellow line there, but anyway. So you just kind of FOIL that out, and you get 1 plus 2 sine theta plus sine squared theta. So we have to use the identity. Now I'll come down here. So sine squared theta is 1 minus cos theta over 2. Now there's different ways you can do this. You can split these up as individual integrals. This is just the way I do it. But I'm allowing for the fact it could be done a little differently. So you see that we have this 2 here. So what I like to do is I like to take these 2 terms and make them have the denominator of 2 by multiplying them both by 2 over 2. So I take 1 and multiply it by 2 over 2. I take this one and multiply it by 2 over 2. That way everything is over 2, so I can bring out another 1/2 to join this 1/2. So now obviously this doubles. 2 times 1 will be 2. 2 times 2 sine theta will be 4 sine theta. And then just 1 minus cos of 2 theta. Like I said, that 2 is automatically gone with the other 2's. That's just the way I do it, just to get out of fractional form. Now before I integrate, I'll just kind of add the 2 plus 1 to make 3. I didn't rewrite an entire line just to rewrite it as a 3. But now when I integrate that 3, that's where this 3 theta will come from. So now we're taking the antiderivative. Antiderivative of positive 4 sine theta will be negative 4 cos theta. Antiderivative. And then the antiderivative of this just has a subtraction sign. Cos theta is 1/2 sine 2 theta. They just both happen to have a negative in front. And put in 2 pi. 2 pi, 3 gives you 6 pi. Put in 2 pi will be minus 4 cosine of 2 pi is 1. So it makes that negative 4. and then sine of 4 pi will be 0, so that's a 0. Over here, we'll put in 0, we have 0. Put in 0 here because we have a cosine. You know, we're used to seeing problems where everything is 0 down there. And put in 0 here, you get another negative 4. So what happens here, you have a negative 4 minus a minus 4. Those cancel. And then you have 1/4 times 6 pi, and that gives you 3 pi over 2. All right. So I decided to do another cosine here. Yeah, I just got some graphs down there. Just I thought I'd do a second cosine one because that one's, you know, just slightly trickier compared to the sine. That's why I didn't do a second one for the sine. But this one, you know, because I'm doing that whole half thing again, half petal, then doubling it. So find the area of one petal for r equals 3 cos theta. So I'm going to start with 0. And I'm mentioning that the radius is 3 here, which I'm not sure why I didn't mention that, but that's all right. Not critical. So I want to figure out where it gets back to the origin and completes that half petal. So I got it written this way. So cosine of 4 theta, I want to know when that equals 0. And I know that will happen at pi over 2. So cosine of pi over 2 equals 0. Therefore, 4 theta equals pi over 2. And theta will be pi over 8. And over here, I'm just showing like I was in that other problem. I'm going to confuse you with this, but as if you didn't want to use the doubling factor there. So then you would say it equal to 3 pi over 2. So you're either going to go from 0 to pi over 8 and double it, or go from pi over 8 to 3 pi over 8 without doubling it. I always like to do the 0. So there's the little magical 2 there because we're doing half a petal. That will cancel out the 1/2. So we go from 0 to 3 pi over 8. 3 cos theta, 4 theta squared gives me 9 cos squared 4 theta. Use the identity again. Going a little faster on this one. The 2 will come out, makes that 9/2. So we'll have 1 plus cos of 8 theta. So the antiderivative will be theta plus 1/8 sine of theta. Put in pi over 8, put in 0. And we have 9/2, put in pi over 8. And then sine of pi will be 0. The bottom one will all be zeros. So you get 9/2 times pi over 8, which gives me 9 pi over 16. And I believe I just have some graphs down here. I guess I was just having a little fun here. Oh, okay, this one actually was doing something specific just to show that it was graphing. Yeah, because I can't really, well, I guess, yeah, I can do that in the calculator by setting the range of values to plot for theta from 0 to pi over 8. I guess I could have done that here, but I guess I was already doing something in Maple, so I just stayed with that. And this one I had to complete the entire graph, so so I did half the petal, we doubled it, and then instead of doing the full petal. But anyway, long story short, if you look over here, that 0, using 0 to pi over 8 like I did, got 9 pi over 16. Or if I would have left the 1/2 there and did pi over 8 to 3 pi over 8, would also give me 9 pi over 16. So, all right, that concludes this video on area and polar coordinates.